Hi, I'm trying to start videos without saying so. It's not working very well, but this video is going to cover an example of MTMM and work through the all the steps for MTMM and talk about how do you interpret the output that you get. So first thing we're going to do is import the data, and now on MTMM you usually need the entire data set, especially because when working with some of this you'll end up getting Haywood cases, so it really helps if you have the whole data. And it's not like when you have the whole data you won't get a Haywood case, but sometimes it helps because the variance is sort of easier to estimate rather than just relying on covariances. Okay. So I included a data set for you to work with. This is not the best example of MTMM in the sense that it won't work like it should, but that's okay too because you can still learn from it. So we're going to use read CSV, or you can use the import button in RStudio, and I don't need to name anything because I pulled in the entire data set. So what I've done over here, I want to load our libraries, is, let me clear out the last example. I've set my working directory to where I know this file is hidden, and then I just use read CSV. Now one thing you want to do is, one, you really shouldn't call your data data, but lessons learned the hard way. One thing that you can do is if you do import data set and then find the data set here, be sure you click yes for header and then hit import. And then when you have that kind of data set, copy and paste the code that it gave you when it imported the data set and stick that at the top of your R script, because having the data saved at the top, if you screw something up during data screening, which we're not showing in this video, but you would do, you can re-import the data set kind of quickly rather than import data set, blah, blah, and having to click 1,000 times. Okay. All right, so what I'm going to do to start is define my model and build a methods CFA and a traits CFA separately. So I gave you the example here, and I made this example up. These are two scales, the Purpose in Life test and the Meaning in Life questionnaire, that are both about purpose/meaning. And they each have 20 questions, but then I picked questions from them that are very clearly meaning-based, very clearly purpose-based. And so the joke on this is that really it's one big thing called MERPUS, and you'll see that in this example, where the traits are so highly correlated we probably should consider them to be the same thing. And so, brain fart, what we're going to do is take these particular items and build a traits-only model and a methods-only model just to kind of make sure the whole thing is even going to run before we start the steps for MTMM. So we're going to build methods-only and traits-only to get our measurement models, and then we're going to look at how those worked. So I've got my methods only, so the MLQ is made up of all the M questions. The PIL is made up of all the P questions. So I'm not using the entire data set. There are more questions than this. So here's my methods model. Now my traits model, the meaning questions, I have half M's, half P's, and the same for purpose. So when you're building these two things, make sure that they're not the exact same model, because when you put them together here in a second, it will blow up if you try to build the same thing twice. So with methods, all the methods should be together, but when you get to traits, it should be half and half. So each question or item should have 2 arrows going into it in the full model, one from traits and one from methods. Let me close that. So here's my methods CFA, and you'll notice that it's the model, data equals data, standardized equals true. I have turned that on in this example because we will have to use that later here in a minute. And so for MTMM, it's just easier if you start with standardized equals true. I know this whole semester I've been like, don't do that, but you can turn it off if you'd like. But here in a little bit, we're going to have to leave it on for some reasons you'll see in a second. All right, let's look at a summary here. So for my methods, let's look. We've got an okay model. Okay. Now methods, I don't know that I necessarily need this model to fit very well. Traits, it really should fit well. But for methods, like, yeah, these items go together, but it might be that these two items are better together because they're the same trait. So it's okay if this model doesn't fit too well, and it fits, it's sort of mediocre at best. Okay. And what you'll notice is some of these actually are negatively correlated with their own method. And so that's going to be an issue for us later, is that some of these items are negatively correlated and they're not supposed to be reverse coded. I have fixed all of those already, so it's interesting why some of these items are negatively correlated with each other. Now for the pill, they're all nice and strong. So I think the problem really here is an MLQ. Now they are very highly correlated between the two because these scales measure roughly the same thing. All of our variances are positive, good, and then all of our R-squareds are less than 1, so we didn't have any Haywood problems. Okay. Because this is in my final thing I'm interested in, I'm going to actually skip modification indices and residuals. I am more actually interested in traits. So let's run that. Okay, first let me look at my methods. Picture, this looks good. Now let's try traits. Okay. Now for traits, it actually gives me an error message. So that's no good. Let's look at what that looks like. So I've got inspect, okay, traits fit, comma, let's do core.lv, because I can interpret correlations a little better. Okay. So first problem, these traits are so highly correlated that it estimated that correlation over 1. No good, right? So this model is problematic before we start, mostly because they're so terribly correlated. Okay. Now if I run my overall model here, it's interesting because they're really highly correlated, but the fit is not very good. It's probably a little worse than the previous one. And one issue that we're going to have is that some of these indicators are positive and some of them are negative, and they do work better if they're all in the same direction. It is not that they can't be negative or positive, but if you want to talk about reverse-coded items and you're here at MSU, you can go talk to Dr. Vizio, and she will read you the riot act about how much she hates them. But it does cause some issues because you're trying to calculate things that are strongly positively correlated, and then some of them are negative, but they're not negative like to all of the items. So why is that happening? Sometimes it works, lots of times it doesn't. But we're gonna run with this thing. I know it's not perfect, but it's an example for MTMM, and you can kind of see how MTMM is supposed to work, even though this example isn't necessarily the best one. But all of our variances are at least positive, and all of our R-squareds are less than 1. This correlation is the problem, really. And what you can see is actually we do have some items that do not predict their trait very well. So that's another issue. So for purpose here, we've got 2 items that we should potentially drop because they're not really doing me a whole lot of good. And I would actually never run this model in particular this way because I know that's not really where those questions are supposed to go, but this is just an example. Alright, if I wanted to see, let's see modification indices here. Scroll, damn it. There we go. Sort equals true. Let's see what it would tell me to fix. The first thing it would actually tell me to do is correlate a lot of errors. So look at all these error correlations. That's pretty much the entire, finally down here does it tell you to cross-list something. So there are some problems with maybe some of these questions are so highly correlated that it doesn't know what to do with them. So if I were trying to fix this model and not show you an example, I would start by looking at some of these questions. And I potentially would start dropping questions that do not predict their own trait. So let's look at a picture of that one. So now I've got meaning and I've got purpose, and I've got every single item here. And so potentially maybe this is a 1-factor model. Okay. But a one-factor model does not work for multi-trait, multi-method, so we're going to keep running with 2 just so we can look at an example here. So the first model that you will do in a MTMM is take your methods model that we've just built and the traits model and combine those 2 together. So we're going to put both of them into the same model, and we're going to fix the covariance between traits and methods. Traits are still correlated, methods are still correlated, but no cross correlations. So to do that, there's no orthogonal code, because orthogonal only works for like bifactor models. That turns all of them off. And so I have tried, I think, before to do orthogonal equals true and then turn them back on, and it gets grumpy with you. So it's easier to just turn them off when you don't want them. So we're going to do methods is uncorrelated with traits, so 0 times the trait. If you look at that code here, I've got methods, traits, and then here I'm fixing the covariances. So I did MLQ to meaning, MLQ to purpose, pill to meaning, pill to purpose. I left MLQ to pill alone, even though it's going to be a problem, and meaning to purpose alone. Okay. So don't turn them all off, just turn off the ones across methods to traits. Let's run that, see what happens. Okay. Now, interestingly, when I put them together, it stopped freaking out. So when I ran traits by itself, it was like, bleh! But when I have both of them together, some of them, I think what's happening is some of the super high correlations it doesn't know how to deal with traits only went to methods. Just a guess. I don't think you should probably hope that that happens if your first model for traits is poor. You should figure out why it's poor first. But let's look at a summary here. And scroll up. And look how pretty this model is. I don't know why this one works so well, but look, the fin indices are really lovely. RMC is great. SRMR is great. All of our things are loading kind of. I don't want them to load on traits, so I'm going to come down here to methods. M2. I'm sorry. I want them to load on traits, not methods. So I'm going to look at traits. M2 sort of meh. It's significant, but meh. And then this M8 question here, also meh. And M3. So I've got a couple questions that maybe aren't so good. My cross correlations are 0, that's good. My MLQ and pill are only slightly correlated at this point, so that's nice. It took the correlation between the methods and moved it over to traits. And if this is true, that's why that last model is not running very well, because it is multicollinearity out your ears. That is very high. You really should collapse these into one. Okay. And this is just data I happen to have, so that's why we're working with it. Okay. Our variances are good. Our squareds are greater than, or less than 1, rather. Okay. So what we're going to do, and let me create the picture. We were here. So in this picture, what I can see is every square has 2 arrows. Great. And then meaning predicts half of them. And, I'm sorry, traits predict half and methods predict half. And it won't line them up pretty for you with one side on each side. But this, at least, I can't read any of the numbers. But at least I can see it looks like it's doing it correct. Now on these, I included this code because I've been kind of cutting and pasting it as we go, but I really would just use it for fit indices, and I don't know that you would really want to modify anything in this model. If you were going to do some modifications, it probably should have happened earlier, because the purpose of MTMM is to compare models to each other, so I don't know if I would modify them on each individual level. But I have been kind of cutting this code so that you'd have it in each one. Probably not going to use it in this example. So let's fill in model 1 here. So chi-square, let me run this here. So our chi-square here with 73 degrees of freedom. So these often have very large degrees of freedom because they have lots of squares. Our rim C is 0.042. Okay, SRMR 0.024. And our CFI somewhere 0.983. Now we would hope that model 1 is going to be the best model. So this is correlated traits and methods, not cross-correlated, just correlated. And this hopefully is the good model. Yes and no, as you will see coming up. So for model 2, we've actually already run this model. We're going to delete those traits and just look at the methods. And so we've actually already done this, but we're going to run methods only and just look at the relationship here and make sure that the inclusion of the traits makes the model better. And I think if you remember when we first started, I said, yeah, this model's okay, and the fit indices are poor, but that's because we really don't want traits, methods to be the reason why they work. We want traits to be the reason why they work, not methods. So let's do that. So I copied my methods model from earlier. We run that, no errors. Let's look at a summary here. Positive variables, less than 1, positive, no Haywood cases it looks like. You know, we've got some questions that are sort of iffy. But I can see if I look at my fit indices here, let me go back to this one and just do it all in this one, that the RIMC is much worse. SRMR is also going to be much worse. My CFI is poor. Okay. And my chi-square here, this one, with 89 degrees of freedom, because we deleted a lot of predictors, is very much terrible. What I could do if I was interested in the differences between them, let me type down here, dang it, is run an ANOVA. So I would do model 1, model 2 to compare model 1 and model 2, but remember, don't do this. So it's going to be very tempting here in a minute to do this. That does not do what you want it to do. Okay, so the way the ANOVA function model comparison works is it's going to compare model 1 to model 2, and then in the second line it would compare 2 to 3 and 3 to 4. It steps down. Remember, we're comparing everything to 1, so we're going to have to run that comparison one at a time as we go here. Okay. So let me look here. Make sure my picture looks correct, and it does, and I'm going to add that ANOVA right here. So I'm going to do model 1, model 2. Okay. And it does not like that. Oh, model 2.fit, my bad. Okay. It didn't like the fact that I tried to run it on the model and not the CFA. So it didn't like trying to compare characters. So it is a significant difference. It's got 16 degrees of freedom and a 900 chi-square, so that would be significantly different. And if I look at the numbers here, model 2 is much worse than model 1, which is good. That's what we want. So the addition of the traits is a significant change, which means that those traits are important, so it's convergent validity of the traits. If I did my CFI test, remember it's 0.01, and clearly there's a significant drop in fit by the excluding the traits, which implies that our traits are important. Good. Now let's try model 3. We're going to perfectly correlate those traits and make sure this model isn't very good, because otherwise why would you have multiple traits? As you will see, this model is going to be good, and that's a problem, but this is just an example. So what it looks like for model 3 is I'm going to go back to the code from model 1. So this is all the code from model 1 all the way through here. Where am I at? Okay. But we're going to fix that trait correlation to 1. So tilde tilde 1 instead of brain farts, instead of the we're not going traits to methods or anything. So the first ones are set to 0, this one's set to 1. Now, why have I been using standardized equals true? Especially because most of the semester I've told you not to do that. And this is one place that it really matters, is because we want to set the correlation to 1, and if we leave a standardized equals true off, that's going to set the covariance to 1, which is not what we want. So this will force this to actually be the correlation being set to 1. It doesn't tend to matter too much, but at least this way I know I'm setting the correlation and not the covariance. Okay. So let's run Model 3. Model 3 is going to look lovely because they are so highly correlated. So be sure you set the traits correlation to 1 and not the methods. So I did that right. All positive, all less than 1. Scroll up here. So let's look at our chi-square here with 74 degrees of freedom. So our degrees of freedom went up 1 because we fixed that parameter as opposed to estimated it. Okay. So our RMC 0.042, 0.024, this isn't changing just a whole lot. It's actually all the same, I think, which is no good. You want this model to be worse than Model 1 because that implies that the traits are discriminate. They're definitely different things. And in this case, they are not different things, though. Which is pretty clear to see looking at those fit indices. But if I add some ANOVA code, so Model 1 fit Model 1, remember everything's compared to Model 1, you will see that they're not significantly different from each other. Damn, that's no good. We want this comparison to be different, which implies that the traits are different things. But just to make sure I'm doing this right, I'm going to run my code. And it's really tiny and hard to see, but you can see here that this variance, if you get really close to your screen and squint, is set to 1. Oops, Sanova. All right. So the last model we're going to do is set the correlations between methods to 0. Now for Model 4, remember, this is the weird step. We want it to be non-different. So we want Model 1 and Model 4 to show no significant differences, which implies that those methods are unrelated after accounting for traits. And you would want your methods to be unrelated, implying that both methods are worth the trouble of using. One caveat here is to be careful that when you go from programming Model 3 to programming Model 4 is that you don't copy 3 and then make 4. You should go back to Model 1 and then add the code that specifically turns off the traits, sorry, I keep saying the wrong one, that turns off the methods correlations. So don't run Model 3 with perfectly correlated traits and then add no correlation for methods. Remember, we're going back to Model 1, not going down in steps. So multi-group models and latent growth models do this like sort of step down or step up procedure where each model is compared to the next one. MTMM is everything's compared to the first one. So we should get this picture, which is very tiny, but has 0 correlations between traits. No, methods. We're on methods now. Traits we don't want to be perfectly correlated. That's step 3. Methods we want to have a 0 correlation. That's step 4. It gets confusing. So let me go back to the table I've been filling in. Here we go. Let's try running that. So I went back to Model 1 here, so these first 6 lines or so are Model 1. And you'll notice I added a non-correlation between PIL and MLQ, which is our methods. I do not have this line with a perfectly correlated trait, so leave that out. So we're going to run that. I'll run our summary here. Remember, we want this model to be good. So down here, it's still got meaning and purpose as way too highly correlated, but it turned off this correlation here. Here we go. So we want this model to be comparable to Model 1 because that implies that the methods are uncorrelated, and if methods are uncorrelated, that means they're both useful things. If they are perfectly correlated, if the methods are correlated, that implies that they are measuring the exact same variance, so they're not discriminate from each other. So let's look at CFI 0.983, it's the same one. So our CFI hasn't really changed. Our RIMC and SRMR look the same. Our chi-square looks pretty close. Let's see if it is different. So we're going to do ANOVA, model 1 fit, model 4.fit. Okay. And it is not significantly different, which is good. That we did want to have happen. So after you control for the traits, the methods are unrelated, which is good. That means that the two different scales are measuring different things. Or they're measuring purpose and meaning in the same way, but they're not so highly correlated that they're the exact same scale. So that would be a good thing. So this doesn't really pass the rules for MTMM because it should be purpose and not meaning and purpose separately. But at least the damn thing ran. So other examples I have of MTMM never seem to stupidly run, so this one will run, although it's not the best model. The other thing we're going to end with is an interpretation of the parameters. So we're going to fill in this table. Now, I made this table for you guys, but and it goes, it's a little too big is what it is. But remember that you're gonna, if you're doing one of these on your own, what you do is you just list all the items down the side. So make yourself a list of every square that you have, and then put X's where they don't go. So these are all meaning questions, so I put X's on purpose. So I have my traits here first, and then I put X's on the method that they aren't. And so I know where to fill things in. And so we're going to line this up with the output from Model 1. Because in a perfect world, Model 1 has been significantly better than 2 and 3 and not different from 4. And so we want to look at this for Model 1. Now, if you want to program a correlated uniqueness model, which we won't totally have an example of, you would also do this. So this is how you can interpret in the 4-step Widaman procedure or in a correlated uniqueness sort of way. So let's go back and look at those parameters for Model 1. So we'll scroll way up here to the top. And this is the standardized solution. So I could use either the estimates or the standardized ones, or I can use standardized all, but it's all about the same. So what we're going to do is take these, all these here, and enter them. 2 shakes. Okay. Nothing important. So I'm going to copy that and kind of enter them one at a time. Can I split screen here? Let's see if we can make this happen here. Shwink. Shwink, shwink, shwink. Ah, wrong button. Can I get smaller? There you go. Computer issues abounds. There we go. So for meaning here, for the first one, so MLQ to meaning 1 here. So that's MLQ, sorry. I'm going to come over here. The estimate is negative 0.07. Okay. You can do 3 decimals if you want. For 2 here, the estimate's 1.26. So I might like it to be standardized, but it doesn't matter. These are all in the same scale. If they're not in the same scale, you should make sure it's standardized. I like looking at standardized all a lot because it's similar to EFA, but in this particular case, I know it's at least standardized on the latent variables, so they're all, even if they weren't in the same scale, they would still be standardized. So here's M3, so I'm going to come down here to M3. Okay, this does take a little bit. Fortunately, you got to watch me struggle through it. So I got 1.36. M4 here is 0.01. M6, oh wait, this next one's M5. So negative 0.04. M6 here is negative 0.10. I think I've already screwed this up. Oh, no, oh you good. 7 I skipped. 8 is 1.332. 9 is negative 0.06. Or 7 if we round up. And then 10, 1.30. So they're kind of all over the map. Let's see. I think purpose is next. So pill here. So 3, 7.71. And then 4 is 0.44. Lost my mouse. There we go. And then 8 is 0.46. 12 is 3.4. 17 is 2.6. And then 20 is 0.63. Now let's look at how they're related to their own particular factors. So I've got meaning here is 109 for ML1, M2 is negative 0.141, M5 is 0.9899 if I round up, 10 is negative 0.75, P4 is 0.66, P12 is 0.82, P17 is 0.61. Come over here to the MLQ1. So for purpose now, so I've got M3, it's negative 0.16. So that's not good. 1.15, 6 is 1.15. Wait, did I read the wrong one? No, they're the same. Okay, negative 0.27, 0.98, 0.49, 8.44 and 0.69. Okay, all that struggle bus, but now let's look at it. So what do I want to do here? Well, when I'm looking at this, I want to make sure that the traits here are higher than the methods. And so as I go across here, 109 is bigger than 0.07, great. Negative 0.41 is very much not larger than 1.27. So this one is a problem, because the traits should be larger than the methods. Okay, that's why I put them on the left side. 0.99, much larger. Negative 0.75, not absolute value-wise larger. 0.66 is bigger, 0.82 is bigger, 0.61 is bigger. So the pill questions all did fine. This question is not so hot. It doesn't really load very well on its factor, and it definitely is much better for the trait. These two are good. This one is poor in the same way. This one's good. This first one is not good, but at least it loads on its trait. Second one's equal, and the third one's equal. So on these, they're sort of equal. And then it's sort of hit and miss. So it's like half and half. And part of that problem is, I think if this were one factor, it would be a little better, but that's how you interpret it. So you really want more than half of them to be, the traits be much larger than the methods. There's no hard and fast rule for this, but in a perfect world, they're all bigger, because the trait accounts for all the variance and not the method. And then, whoo, that's tiny. Why is it so tiny? But anyways, let's look at that trait correlation. So for meaning and purpose here, let's make that a readable font. we already saw that that was like really high. There we go. So the correlation between meaning and purpose, so that's here, is 0.99. Okay, so this is bad because it's 1 effectively. And that's what we saw when we ran Model 1 versus Model 3. If we come back over here and look at the methods correlation, I got negative 0.15, and that's good. Right, so this is good because it's close to 0. And that's what Model 4 was comparing. So overall, what happened? So does our model meet the steps for MTMM? Well, mostly. 1 versus 3 is not significantly different, and that's pretty clear from the problems that we had when we ran our traits, that maybe we need to reconceptualize those traits because this didn't work very well. Okay. The parameters also supported that notion because some of them do not load on their trait just at all. So these two don't load on their trait. Some of them are negative, which may be causing us some problems. And they should load much better on their trait than their method. You know, give or take a couple of, some of them that just aren't will load kind of on both pretty well. It would be better if they were all traits over methods. And so I would say the parameter interpretation supports the fact that we didn't really get that difference because we see that the correlation between the two traits is way too high and the correlation between methods is actually nicely low. Okay. So the interpretation of parameters confirms the steps for Widaman procedure. If you're doing correlated uniqueness, you would use, for this table, you could use the trait loadings and then look at the correlations between the errors and make sure the trait loadings are higher than the correlations between the errors for each particular one. Because you won't have just like one loading, because remember, all of these questions, all the M questions will be correlated together. But you would want those trait loadings to be high and the correlations between the errors to be low if you wanted to program a correlated uniqueness model. To type one of those things up, what you would have is just lots of, instead of the methods latents, you would have lots of lines correlating those traits because you'd have to do them pairwise, one each, like MLQ1 to MLQ2, 1 to 5, 1 to 10, 1 to 3, 1 to 4. So you would have lots of individual lines to program that sort of thing. Okay. So together, all of that is MTMM using the Widaman steps and then some interpretations of parameters if you wanted to look at those rather than talk about steps specifically.